Okay, welcome to the video from the Applied Mathematics course for A-Level Year 1, Chapter 4 on correlation. Okay, so far in Chapters 1 to 3, we've looked at data that only has one variable. We call that univariate data. We're now going to introduce data points that have two variables. So, for example, if you were testing a group of people, you might take their height and their age. Okay, so two variables attached to each person. We might want to consider the relationship between these variables. Okay, when there's two variables attached to each data point, we call this bivariate data. Right, in 4.1, which is this video, we're going to look at correlation, and the definition of that is the type and strength of linear relationship between the two variables. Then in the next video, in 4.2, we're going to look at linear regression, which is applying a model to that data so that we can interpret it and use it to interpolate different values. Okay, first correlation. So a recap from what you would have done in GCSE. So there's two things that you can talk about when it comes to correlation. You can talk about the strength and you can talk about the type. So if we first of all consider this graph on the top left-hand corner here for English score versus math score. Now you can see the data points are following a general trend where it's going from bottom left to top right. So we call this type of trend a positive correlation. Okay. However, these data points, they're not very closely aligned. They're not very close to a straight line. So we'd say that's a weak positive correlation. Okay, this one over here, we've got age versus the weekly time on the internet. Now, these data points are going generally from top left to bottom right. So we call that a negative correlation. Now, again, they're not close to a straight line, so I'm going to call that a weak negative correlation. Bottom left down here, bottom left to top right. So as distance goes up, the cost of the fare goes up. So it's positive. And this time it's very close to a straight line, so we can say it's a strong positive correlation. And then the final one down here, the number of people in a city called Dave and the crime rates. Well, there doesn't seem to be any sort of pattern whatsoever. So we can fairly confidently say there's no relationship between the two, and therefore there is no correlation. Okay, so a little bit more terminology here to do with the variables. So we've got two types of variable. We've got the independent variable or the explanatory variable, which is generally the one that's controlled by a researcher or a scientist in the lab. Okay, and that variable goes on the x-axis, and it's quite often the one that might cause the relationship, explains the relationship, explanatory variable. Then the other variable we call the dependent variable or the response variable, and this is the one that's measured by the researcher. Okay, so what happens when you change the independent variable? What happens to the dependent variable? And that is generally plotted, or it is plotted, on the y-axis. Okay, so let's have a look at a few examples of this. Go onto this screen here. Right, so when considering statistics, and particularly correlation, it's really important to use common sense. Think about the relationship between the two variables that you've got. Okay, don't just jump in and interpret those without thinking about them. Okay, so for each of the pairs below, I want you to have a think, which is the explanatory variable, or the independent variable, and which is the response stroke dependent variable, and what would you expect the correlation to be? Okay, so the first pair of variables here, the price of housing and the distance it is from a city centre. Which would be the independent, which would be the dependent, and what would you expect to see in the correlation? Okay, well, the one that we can control is likely to be the distance from the city centre. We choose where we would get that information from. We choose the locations. Okay, so we call this the independent variable. And the price of housing is a thing that we're going to check up on, we're going to research. So that will be the dependent variable. So I'm just going to do D for distance here, P for price here. Obviously, if you're doing it properly, you'd label it properly. So what would happen? So as it gets further from the city centre, I would expect the price of housing or the price of land in general to decrease. It's in less demand. Okay, city centre, you want lots of people want to live there, or lots of people want to have businesses there. Whereas further out, there's more space and there's less people that want to live there. Okay, so I would expect it to look something like this. I'd expect there to be a negative relation. Okay, negative correlation. Right, next set of variables. Have a think about these. Hours spent revising for a test and the score that you get on that test, which is independent, which is dependent, what would you expect to happen? Okay, well, the thing that you can control to start off with is the hours that you spent revising. Okay, so I would put that, let's call it H, on the x-axis for the independent variable. The thing that results, the thing that responds to the hours of revising is the score that you get on the test. And I would expect the more hours revising, the better the score that you get on the test, so a positive correlation. Okay. Right, those two are fairly straightforward examples. Have a think about this one here. The number of ice creams sold at the beach and the number of sunglasses sold. Which is the independent? Which is the dependent? What would you expect the correlation to be? Okay, this one is a lot less obvious. Okay, I'm not convinced there's likely to be a causal relationship. So if I sold more ice creams, would that automatically mean that more sunglasses were sold? Or if I sold more sunglasses, does that ultimately mean people go and buy more ice creams? No, it could be, and I think it's quite likely that if there are more sunglasses sold, there are also more ice creams sold, but they're not causing each other. Okay, there's no causal relationship between these sunglasses and the ice cream. So I'm not sure you can actually assign an independent and a dependent variable. And actually, if you were looking at these, you'd have to question why are you looking at these? What is it that's actually causing them both to go up at the same time? Okay, so this is an example where correlation doesn't always mean causation. And we'll talk about that more after one of the examples shortly. Okay, going on to some of the examples from the book. So the first example we have here, we've got a study of a city and the population density and the distance from the city in kilometres. Okay, so we've got the distance here and we've got the population density here. Okay, so part A is to draw a scatter diagram to represent this data. So the first thing we're thinking about is which one is likely to be the independent variable. Okay, which one is the explanatory variable? And the thing that you're choosing here is where you're selecting the data from. So that's going to be the distance from the city centre. So that's going to go on the x-axis. And then population density is the thing that you're researching. So that's the thing that's going to go on the y-axis. Drag this down a little bit. So you're going to have to go up to a maximum of 4. Quite often it's a good idea to go a little bit higher. And here. Okay, so this is going to be the distance. Make sure you label it properly. And then the population density, the dependent variable, goes on the y-axis. And the units there is people per hectare. What have I missed there? Okay. Then, as you would have done in GCSE, you're going to plot each data point. So for point A, you're going to go to 0.6 and then up to 50. So that goes somewhere up like that. For point B, it's 3.8 and 22. 3.6, 7, 8, 22, I think is there. Okay, and you carry on and you plot all those pieces of data. I'm not going to go over that, but you can do that, obviously. Okay, so here is the final plotted data. So I've plotted with dots here. It then says, describe the correlation between the distance and the population density. So as you can see, the general trend is it's going from top left down to bottom right. So the correlation is just going to be a weak, because it's not particularly close to a straight line, it's going to be a weak negative correlation. So whenever it asks for correlation, those are the two things that you need to state: weak, negative correlation. Okay. For part C, and this is where students sometimes don't understand what they have to do, it says interpret your answer. So interpret your answer means to actually describe what's happening, describe the relationship between the two variables, the distance and the population density. So you need to use those actual words in the question, in your interpretation. So as the distance increases, always start with your independent variable. As the distance increases, the population density decreases. Okay, and that's what you'd write. Example 1 done. Right, on to example 2, and this relates to what we were talking about on that back here when we were looking at the number of ice cream sold and the sunglasses sold. Okay, and it's talking about the relationship and whether it's a causal relationship. So just going back to what we looked at here, the distance from the city centre caused the price of housing to go down. The amount of hours you spent revising caused the score on your test to go up, whereas the number of ice cream sold didn't cause the sunglasses sold to increase. Okay, so this is something you've got to think about and something that's really important. Okay, so example 2, Hideko was interested to see if there was a relationship between what people earn and the age at which they left the college education. Okay, she asked 14 friends to fill in an anonymous questionnaire and record the results in the scatter diagram. Okay, so here you've got what roughly looks like a negative correlation, but quite a weak negative correlation. Describe the correlation between the two shown. So for A, I'd write a weak negative correlation. Part B, Hideko says that her data supports the conclusion that more education causes people to earn a lower hourly rate of pay. The more education they do, the less pay they get. Now, looking at the graph, that possibly appears to be the case. However, considering the context and considering sort of logic, you'd actually expect if you had more education, you would get a higher salary. And really, what's quite possibly happened here is that the people that have left school at the age of 16 or 18 have gone straight into a job and they've started to earn money and they've started to make their way up the pay ladder. Whereas the people that have gone to university and have got a higher level of education have only left college, only left university when they're 21, 22 years old. They're just starting a new job, therefore they're only getting a lower hourly rate of pay at the moment. But as you'd expect, then later on, as they get more experience from that job, and to rapidly progress up the pay rate because they've got that higher level of education, they've got those higher qualifications. Okay, so give one reason why Hideki's conclusion might not be valid. The reason it might not be valid is because respondents and they actually, no, that's right. Who left education later would have significantly less work experience. This could cause a reduced income at the time of the research. Certainly not the fact that they've got more education. That has not caused them to earn less rate of pay. Okay, make some notes on those examples if you need to, and then go on to exercise 4A and complete that for me.